Hello everyone. In this video I will go over on how to simulate a turbulent flow inside a pipe using a time and a space varying boundary condition, and also create some animations from the output. So let's start by reviewing the geometry. As you can see, our geometry is just a simple rectangle that has been drawn on XY plane as a sketch 1. Let's check out the dimensions. The diameter of the pipe is 20 millimeter, and the length of the pipe is 100 millimeter, which is drawn at the center. And I have used the option surface from a sketch to create this surface. An important note here is that to define this surface as fluid, not solid. And also I have used name selection option to define my inlet and outlet. My inlet is on the left side and outlet is on the right side, which has been defined using a name selection. So this has been a quick summary of my geometry. Let's move on to mesh. But the element size of my mesh is 1 millimeter. My geometry is really simple in this demo video, but in case you want to enhance the quality of the mesh, you could use a sizing option to define the size of the mesh on each side of the rectangle. But we will just move on with this mesh. Let's check out the setup inside the FLUENT. We will start with a general menu. So my simulation is pressure based, since I'm simulating a flow which is incompressible. In case you have a compressible flow, you need to use density based option here. I'm doing a 2D simulation, and that's why I have chosen planar. And I want to check out the time progression of the flow over, and that's why transient is selected here, and I'm not considering any gravity. Let's check out the models. For models, I have changed the laminar assumption to a turbulent flow using K epsilon model, and also enhanced wall treatment. This is my turbulence model. My material in this flow is air, but in case you need to simulate other fluids, you could use this material menu to define it by selecting create edit and using the FLUENT database. As you can see, plenty of fluids are defined here as default. In case your fluid wasn't available there, you could use this properties box here to define your fluid of choice, and then select change create. I'm not going to do it here because I'm just going to do it with air. So that was the material section, and now let's move on to important boundary conditions. Let's double click on boundary condition. I'm gonna need to assign two boundary conditions here, inlet and outlet. For inlet, I'm gonna use a velocity inlet, and let's click on edit to assign it. So my velocity magnitude here is going to be time and space varying. and it's not going to be constant. So to apply that, you need to select this pull-down menu and use expression option, and then select this f of x to write down the function of your choice. As you can see, plenty of functions are available, like sine and cosine and other hyperbolic functions that you can use here as default. Let's review my function. The maximum value of the velocity is going to be 10 meters per second, and this value is multiplied in two functions. The first function is going to apply the time varying situation, and the second one is going to create a space variation. The first function is cosine of pi t. So basically, after 0.5 seconds, the direction of the flow at the inlet is going to be changed, and it's going to fluctuate over time. As you remember, the radius of my pipe was 10 millimeters. So basically, this function is r squared minus y squared over r squared. So it's just a simple second order parabola. Let's use this function. And my outlet is a simple zero gauge pressure. So I'm going to use pressure outlet with a zero gauge pressure Pascal. In case you had any time or a space varying pressure condition, you can follow the same procedure here and select expression and enter a new function for your pressure at the outlet, which we will not do here because my gauge pressure is 0 at the outlet. And let's select OK. So I'm gonna define some output from this simulation. Firstly, I'm interested in the velocity the velocity profile at my inlet. So to define that, I'm gonna use this plot menu and then select on XY plot and select the new. Since I already have done that, let's review the settings. I have named it as velocity profile, and this is going to be the velocity in x direction at the inlet. In the surface window, you need to select the surface or the location that you want to plot this XY plot. So I want it at the inlet. That's why I've chosen inlet. And and then you're gonna have to press save plot. In case you want to write it in a file, you can check write to file as well. Let's also create a contour of the x velocity inside the pipe. So to do that, you're gonna do the same procedure. Right click on contour and then new, which is already done here, and then name it properly and select x velocity. The minimum and maximum variable of my contour is -10 to 10, since the velocity is going to fluctuate from -10 to 10, and then save display. So my contour and XY plot is defined. I'm also interested in measuring the mass flow rate at the inlet. So to do that, I want to use report definitions here. Right click and and then we're gonna have to go to new, and the mass flow rate is a surface report. So let's follow surface report and mass flow rate. Since I already have done that, it's created here. Mass flow rate at the inlet, and then OK. So we are done with defining our outputs. So basically, we're gonna have 3 outputs from this simulation: velocity profile at the inlet, a contour of velocity, and also mass flow rate. I'm also interested in creating animations. So to create animation, you're gonna have to go to calculation activities and then solution animations. Similarly, right click and then new. So as you can see, I have two animations here. Animation 1 is for velocity contour. Animation 2 is for velocity profile, which is defined already. So I'm gonna have two animations here. And then after doing all this, we're gonna have to initialize the flow, which assign the parameters at equal to 0. To initialize, we have two options. Either we need to do hybrid or a standard. For a standard, you're gonna have to know the variable, the parameters at equal to 0. So you can enter them here manually. In case you don't know them, you just use hybrid initialization, in which FLUENT computes some initial conditions based on boundary conditions. So here I have done hybrid initialization, and I'm not gonna press initialize because my simulation has been done already, and I don't want to dismiss it. But you need to press initialize, and then at the final step we're gonna have to run our calculation, to run the simulation by pressing run calculation. In this new window, we need to enter three important numbers. The first one is time step size, which is 0.1 second here. The second one is number of time step, which I have entered as 100. So basically, the flow time of my simulation is going to be from 0 to 10 seconds, and for each time step, I'm gonna do at maximum 20 iterations per time step. If the flow converges before this number of iterations, we're gonna move on to the next time step, and then press calculate, and you will see the time progression of your scaled residuals, which the simulation has been done already in my computer. So let's just check out the results. So FLUENT has created three windows after doing the simulation. So we're gonna go to solution animation playback to check out the animations. Let's select animation 1. Let's select animation 2 to first check out the velocity profile at the inlet, and press just play. So this is the velocity profile at my inlet. As expected, it's time varying. It's oscillating from 10 to -10 meter per second, and it's also a second order parabola. And the second animation is for contour. As you can see, the fluid is just pouring and exiting the domain periodically. And at last, we were supposed to compute the mass flow rate at the outlet, which FLUENT has created this block for us. As you can see, the mass flow rate is also oscillating. And at last, you want to save the animations. So to save the animations, you're going to use the same menu and select on writer record format, and use one of these options. Usually you can use MPEG, which writes the animations in an MPEG format, but I personally usually use the picture files and select write. This option will create Yes, you will create snapshots of the animations, and you could use a third-party application to stitch these frames together and make a movie out of it, and this will enhance the quality of the movie. I usually use a MATLAB to do this. So basically you have two options. You can either use Fluent Animation Creator by selecting MPG, and also select picture files and create some picture, and then use another application to make a movie out of it. And finally, we asked Fluent to write this the mass flow to a file, and that file is going to be saved here in demo file in the folder that Fluent will save the data. You're gonna have to go to DP0, this folder, Fluent, and as you can see, these HSF files are corresponding to the animations, and they are saved here for animation 1 and animation 2, and also this mass flow rate file is also written here. You could use some other application to plot it as well if you are not satisfied with the quality of the plot of the Fluent. So this was a video of the simulation of a turbulent flow inside the pipe. I hope you enjoyed it. Thanks for watching.